Welcome back. In this video, we're going to follow up with our discussion of level curves by looking at how to do calculus on these level curves. Remember, calculus is the study of derivatives and integrals. Can you believe we're going to take derivatives of level curves? Oh my God, exciting. In this example, let's find the tangent line to the level curve z0 equal 4 for the function z equals x squared plus y squared. We begin this problem by recalling what a level curve is. We recall that a level curve associated with the constant z0 equal 4 is the subset of R2 given by L sub 4 of f, which is going to be the collection of all input points to our function such that f of x comma y equal 4. Well, we know exactly what f of x comma y is because it is the function defined here. This is an elliptic paraboloid with vertex at 0 comma 0. When we expand the definition of this, we would see that this is x squared plus y squared equal to 4, and we see that our level curve is a circle in the domain space centered at 0, 0 with radius 2. So we recall this is all input that produces constant output 4. Recall the difference between the level curve and the contour curve. The contour curves were the set of curves in R3 associated with this constant output. In other words, we take all of these x comma y and we tag a third coordinate in that ordered triplet so that f of x comma y was equal to 4. So these are the input points that produce 4. These are the set of ordered triplets with constant value 4. In a bit after we finish our first analysis of this problem, we will actually boot up Mathematica and see how this all works out. What we just saw was that our level curve looks something like this. We've got a circle centered at 0, 0 with radius 2. So here I go 1, 2, 1, 2, 1, 2, 1, 2. And of course I should probably label all these suckers. So this would be -1, -2, -1, -2, 1, 2. And then we'll go ahead and draw the level curve. And this is where I would, if I was really cool, which I am not cool at all. My students are always so much cooler than I am, forever and ever and ever. If I was really cool, I would draw in Mathematica. But for now, this kind of gives me an idea of the level curve that I'm looking at. So this curve would be the set of all inputs that produce output 4 along my elliptic paraboloid. So I can go ahead and label that. And then the problem has asked me to produce a derivative or a tangent line to this. And the way that I'm going to do this is I'm going to choose 2 points. Well, I don't know. Do you want to choose 2 or 3? Let's for now choose the point. Perhaps we choose this one. So what would this be? 2, 0 to find the tangent line. And then later we might choose this one, and we also might choose this one at a 90-degree angle. If you look at the tangent line to this curve, we expect that line to have no slope, which we'll see in a bit, and it should go through that point. So remember, when we look at the tangent lines in general are more special lines, and we can write the equation for the tangent line very similar to the equation of any line. So this is m outside of x minus x naught, and in particular we want the output of the line to be equal to a slope and a point on the line. So there's the point on the line. And then one of the really special things about this is that this slope will be the derivative of the curve where we're thinking about the y output changing in terms of the x, evaluated at the input point x1, y1, so that's the evaluation bar, and then that now is our slope. So this here is our slope. And then, of course, we just multiply that derivative by x1, y1 plus y1. So in the challenge now, in this case, we know what x1, y1 will be because we've set it beforehand. And of course, we want to say, WTF, mate, want to find dy dx for the implicit equation given by this level curve, which of course was x squared plus y squared equal to 4. And one of the things that we can do, remember that the general form of an implicit equation that we spoke about before was to bring everything on one side, so the right-hand side with 0. In this case, if we set f of x comma y equal to x squared plus y squared minus 4, we get that implicit equation. And now the question that we ask ourselves is, okay, if I don't have y specifically in terms of x, well, how in the heck am I supposed to differentiate this? And this is where we might want to go back to some of the work we did in Math 1A, the first quarter of differentiation. When you have an implicit equation and you want to differentiate, we used a technique called ding, 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 implicit differentiation. Implicit differentiation is a technique that we used in 1A to find the derivative dy dx, so the instantaneous rate of change of y in terms of x, when we were looking at an implicit equation. Again, these type of equations are ones where the output variable y is hard to solve for the input variable x. Even though that's the case, we can use this technique of implicit differentiation to find derivatives. So if you recall way back when to your Math 1A knowledge, there were kind of 4 different things that we did to implicitly differentiate. The first one was to take the derivative of both sides of this equation with respect to x. So apply the ordinary derivative operator on the left, apply the ordinary derivative operator on the right. Everywhere we see the the output variable y in this function, we're going to pretend in our mind that it is an explicit function of the input variable. And the way that we're going to do this is every time we see y, you could actually physically write out y as a function of x. And then now this becomes a symbol for y. And you'll see why this is so powerful in a bit. Once we do this, we would apply the chain rule and other differentiation rules to differentiate both sides of the equation with respect to x. Every time we apply the chain rule and we take the derivative of the inside where the inside function is y, we're going to introduce an algebraic symbol representing the unknown derivative that we want, which is called dy dx. At the end of the day, we'll have this algebraic equation with an unknown dy dx in it, and then we'll just solve by isolating this variable. Let's go ahead and do this technique applied to the specific level curve that we're looking at. So here we had our level curve was x squared y squared minus 4 equal to 0. If you're familiar with this, you might not write all those steps down. However, if you're not familiar with this technique or you don't remember it, I would actually write down those steps that you saw on the last screen for yourself in your notebook and then trace out the steps as we do this example. So step 1 was to differentiate both sides with respect to x. So here I'm going to go ahead and take the derivative of the entire left-hand side with respect to x. Of course, because this is an equation, anything I do to the left-hand side of the equation, I must also do to the right-hand side of this equation. The second step of this was to assume that everywhere we see a y, this thing is now going to be y of x. So in the background, we're going to kind of pretend y equals y of x. And I might do this in just a second. So here, when we take a derivative of a sum, this becomes the sum of the derivatives. This was called the Sum Rule of Differentiation. For those of you that drive on the freeway, you use this rule all the time. When a car in front of you brakes, you look at the comparison between your speed and theirs, and then you make decisions on it. So here we go. Derivative of 0 is 0. The derivative of 4, of course, is 0. So this thing goes to 0. This thing goes to 0. Derivative of x squared with respect to x is 2x. And then this is where I want to be a little bit careful. Before I actually take this derivative, I'm going to write parentheses, and then I'm going to think about y as a function of x. Even though we haven't written y as a function of x, I'm going to look at this as now y of x squared. And the reason that I do this is this now is a chain rule problem. Remember, when I take the derivative of a composite function, f of g of x, this is f prime of g of x, the derivative of the outer function times the derivative of the inner function. Okay, so here the outer function would be whatever the inside is squared, and the inner function is y of x. So when I take this derivative, I'm going to say, okay, here we have 2x plus, derivative of the outer function is 2 times the whatever's on the inside, and then now I'm going to take the derivative of the inside function. So this thing would be y prime of x. And then, of course, this is minus 0, which does nothing. We could rewrite this. Every we see a y of x, we could write that as just y, because that was the assumption that we made in our symbolic manipulation. So this is 2 times y prime. This y prime is the exact derivative, or the slope of the tangent line that I'm looking for. So now we have something that looks like, if I want to isolate y prime, I can bring the 2x over to the other side and then divide by 2y. So this would be minus 2x divided by 2y. And of course, this is going to be minus x divided by y. And y prime, well, the assumption was this was derivative of y with respect to x, and this is the exact derivative that we're looking at. So now I have the rate of change of y with respect to x as a function of x and y. When we look at this function, we can now put those back into our original equation. Well, I give myself a solid F for choice of good places to start. Do you see a problem here? This tangent line has no slope, right? In other words, the slope actually just doesn't exist because it's a horizontal line. So the equation for this tangent line, if you were to look at the equation for this line right here, this would be the y equal 2 line. And you can see if I go to compute this tangent line using this derivative, in order to do it, I would take the x coordinate on top and the y coordinate on the bottom, but I would get a 0 on the bottom. And that corresponds to the fact that that slope does not exist, aka this has no slope. Because we think about a slope as the rise over the run. There's no run here. It's only rise. Okay. So that didn't work out well from this calculation, but we could actually look at another tangent line. Let's look at the tangent line that happens if I move along the 45-degree angle. So let's call this 45-degree angle at radius 2. So this is going to be another tangent line, right? And we have to think to ourselves, so that's the line that really just brisks the surface there. Well, what is that point? So let's go ahead and look at another tangent line, and we'll recall, maybe I'll just keep that line up there to remember what the derivative is. Okay, so let's do the tangent line at the point, well, let's see, 45 degrees. I suppose this is going to be 2 square roots of 2, is that right? Yeah, I think that's going to be 2 square. Well, let's go ahead and do this out in our minds here. One of the things I'm trying to teach you in this class is how to think about math so you don't have to memorize it, so that every time you think about this, you can get it. Pretend this was the unit circle real quick. So if this was 1, and then these are now going to be equilateral. So it's not equilateral. These two are equal. So I know that when I look at, let's call it x perhaps, x squared plus x squared is going to be equal to 1 squared by the Pythagorean theorem, which means 2x squared is equal to 1, which means x squared is 1/2, which means that x is equal to 1 divided by the square root of 2. When we look at the same exact idea, but with a circle of radius 2, we can do the same analysis. So we're going to have 2x squared equals the square of the radius, which is 4, which implies x squared would be 4 divided by 2, which is of course 2, and this would mean x was equal to the square root of 2. So the tangent point, or excuse me, the point on the curve where we want the tangent line to go through would be 2 square roots of 2. So this was a unit circle analysis. The moment that we have this, we return to the idea that the tangent line that we were searching for had a point and a slope, and we said this was going to be y equals m outside of x minus x1 plus y1. We knew that m was going to be the derivative of y with respect to x at the point x1, y1, but we just saw in the last part of this video that this is going to be negative x1 divided by y1 based on implicit differentiation. And if we look at this, both x1 and y1 at the point of tangency are going to be the square root of 2, which means that the slope of my tangent line that I'm searching for is negative 1 over 1. I can now look at my tangent line as negative 1 times x minus the square root of 2 plus the square root of 2, which of course is negative x plus 2 square roots of 2. This gives me a way to deal with the tangent line as a scalar equation, but of course in Math 1C, one of the really cool techniques that we're looking at is to do it as a vector equation. And recall, the vector equation of a line requires both a point on the line and a direction of the line. The moment that we know the slope is going to be negative 1, it means that the direction would be the rise over the run. This is the amount I go in the first component, 1. Negative 1 is the amount that I go in the second component. And then the point that I have, well, that point was square root of 2, square root of 2. So now I can get a vector equation that looks like the square root of 2, plus t times 1, negative 1. And then we can finalize this parametric equation for the line by just combining them together. So this is t plus square root of 2, and then in the y component this is square root of 2 minus t. This gives me now the tangent line to the curve, the level curve at the point square root of 2 comma square root of 2. In the next video, let's use Mathematica to confirm this analysis graphically. I'll see you in the next video.